Watch closely. 9 out of 10 students fall into a very specific trap during their exams, and it quietly costs them their top grades. I mean, we're talking about a fatal logic error that seems totally impossible until you actually see it happen right inside a computer's processor. Welcome to this explainer. We're skipping the standard intros today so we can drop you right into the middle of the action. Let's see this mistake before you end up making it yourself. Okay, let's just freeze the action right here. Think about this. If you wrote this equation down on a math test, you'd fail instantly, right? Why on earth would a computer ever calculate that 255 plus 1 equals 0? In the real world, that makes absolutely no sense. But inside an 8-bit system, this is a daily reality. Now, students will often write down something generic in their exams like, oh, the computer just crashes. But that is definitely not going to get you the marks. What we're actually looking at here is called an 8-bit overflow error, and the mechanics behind it are actually pretty fascinating. But before we can solve this trap, we absolutely need to nail down the exact examiner-approved definition of an overflow error. Basically, an overflow error occurs when a calculation produces a result that requires more bits than the CPU's register capacity can handle. Let's break that down into something a bit more tangible. Imagine an 8-bit binary register as a physical row of exactly 8 light switches. The maximum value you can represent when all 8 switches are flipped on is 255. That's basically 8 ones in a row. Now, what happens if you try to add just one more to that? Well, the math requires a 9th switch to carry that one over, leaving the other 8 as zeros. But here's the kicker. In an 8-bit system, that 9th physical switch simply doesn't exist. Now, check this out. You can witness the exact moment that 9th bit is generated and completely breaks the system's logic. If you follow the glowing data streams representing the binary digits, you can see what happens as the addition carries forward a 1 each time. Eventually, a 9th column is demanded by the math. The total becomes a binary number consisting of 9 bits, a 1 followed by 8 zeros. Literally, that's 1 bit more than the absolute maximum capacity of 8 bits. The architecture of the machine simply cannot accommodate it. There's just no room. It's honestly so easy to assume the computer magically holds onto all 9 bits, a 1 followed by 8 zeros. But that's the trap. In reality, the CPU simply drops that extra 9th digit. It literally throws it in the digital trash because it has nowhere to physically store it. So, what's left sitting in those original 8 bits? Just 8 zeros. And that right there is exactly why the computer suddenly and disastrously thinks that 255 plus 1 equals 0. Crazy, right? So, here's an absolutely crucial takeaway straight from the examiners themselves. Listen to this. Simply writing that the computer crashes or an error happens just isn't enough to score full marks in your exams. You have to explicitly state the exact mechanism. You need to write that the extra digit is dropped due to a lack of storage capacity, and that this lack of capacity to carry out an instruction makes the computer processing unstable or causes it to stop entirely. When it comes to exams, technical specificity is your best friend, for real. To guarantee you don't fall into this trap, we like to use an exam-winning framework called the 3-pass mastery cycle. Pass 1 is all about securing your definitions and contrasts, which is exactly what we just did with the 8-bit capacity limit. Pass 2 is rehearsing the sequential process explanations, meaning you can explain that whole carryover logic step by step. And finally, Pass 3 is focusing on exam adaptability and scenario context. You see, examiners don't just want you to regurgitate a textbook definition. They want to see you actively apply it to whatever real-world scenario they decide to throw at you. This cycle brilliantly illustrates that whether you're describing an overflow error or something like the fetch, decode, execute cycle, you must anchor your technical explanation directly to the scenario provided. Let's say the exam question asks about a robotic arm, a banking system, or maybe a smart thermostat exceeding its data limit. You have to use those specific contexts in your answer. You can't just talk about a generic CPU. You've got to explain how the overflow error specifically impacts the banking system's calculations or the robot's movement. Seriously, context is king here. All right, let's test your active retention right now with a rapid spot the flaw challenge. We've got a simulated exam answer here explaining why a simple addition caused a program crash. I'm going to give you 10 seconds to find the missing logic in their explanation. Look closely at how they describe the binary addition. Are they being specific enough? 10 seconds on the clock. Can you find the flaw? And time is up. Let's map this out together. If you spotted that the student just said there was not enough capacity and the program stopped, then bingo, you found the flaw. You have to upgrade that response to the required technical point. To get full credit, you must explicitly state that the CPU drops the extra ninth overflow digit because it has nowhere to store it. It's exactly that level of precision that transforms a standard middle-of-the-road answer into a top-tier response. Let's do a rapid recap to make sure all of this really sticks. Number 1, an 8-bit register's maximum capacity is 255. 2, addition operations can push that total to 9 bits. 3, lacking capacity, the CPU completely drops that ninth overflow digit. 4, this is exactly what makes the computer processing unstable or forces it to stop entirely. And 5, always apply this mechanism directly to your specific exam scenario. Master these 5 steps, and trust me, you'll completely master the overflow trap. I'm going to leave you with this final, somewhat terrifying thought. If an 8-bit overflow error can cause a simple classroom math program to fail, what happens when this exact logic breaks down inside an automated car's safety braking system? Yeah, the stakes jump from just losing a few exam marks to serious, real-world consequences. We're going to apply this exact type of high-stakes critical thinking in our next explainer on automated systems. Keep studying smart, apply what you've learned here, and we'll see you then.